The only thing I wanted to start explaining is what we will briefly cover in about 20 minutes after the lunch. It's going to be a brief discussion about processing using memory, mostly in DRAM, or basically in DRAM, because that's the research that we are mostly doing in our group. And I think it's good to go quickly over some of these proposals that were earlier introduced by Professor Mutlu. Remember that we have already, or we are already distinguishing between two types of BIM approaches. The first one is processing near memory that we covered in my previous lecture, and the second one is processing using memory. And here in the processing using memory techniques, I think it's really interesting to talk a little bit more about what are those proposals that relate to DRAM. Processing in memory, processing using memory exploit the analog operational principles of the memory circuitry to perform computation and exploits the internal connectivity to move data and can leverage the large internal bandwidth and parallelism that is available inside memory arrays. A common approach for processing using memory operations is to perform bulk bitwise operations like AND, OR, XOR, majority, etc. And by using them, it's also possible to implement some more complex operations such as multiplication or addition. I have a few slides here introducing how DRAM works, but I think that this is something that we can skip and very briefly remind you the row clone techniques that were proposed back in 2013 in a micro paper that allows us to do data copy and initialization. Data copy and initialization are extremely important because they are basically in all applications that we can write, and there has been a lot of past work trying to optimize these different operations. In fact, a paper from 2015, ISCA 2015, from Google, for example, showed that memmove and memcopy take about 5% of the cycles in Google's data center. So that's in reality a lot, and that's why it really makes sense to optimize this bulk data copy. I think Onur already showed this slide, what the problem with bulk data copy these days in computing systems is that you need to do the copy through the host CPU. That means moving cache lines all the way to the L1 and then write them back to the memory. And this is high latency, high bandwidth utilization. It causes cache pollution for data that you are not really going to reuse right next, and also has a lot of unwanted data movement. So it's costly in terms of the execution time and in terms of energy. In future systems, we expect that we will be able to do something as simple as this, moving a row directly from one subarray to another subarray or inside the same memory subarray, and this way save a lot of execution time, a lot of cycles, and a lot of energy. And this is the basic idea or the key idea in row clone, in the row copy. First of all, activate one row, which transfers the row to the row buffer, then activate a second row, the destination row, and this way perform the bulk row copy. And this can be done with just 2 consecutive activations at a negligible hardware cost. So yeah, you can see here with a little bit more detail by focusing us on just the 2 cells in 2 different rows. We can see that when we activate one row, the cells in this row start sharing their charge with the bit line, producing a perturbation in the bit line that is later amplified when we activate the sense amplifier, and when we finally activate the destination row, the value in the sense amplifier gets copied into the new row. And that's a basic idea of this intra-subarray row clone or intra-subarray row copy. The row clone paper also proposes a way of copying entire rows, or copying basically cache lines or entire rows, cache line by cache line, copying them from one bank to another bank by using the shared internal bus. And that's what you can do, like more or less like this. And that is still good in terms of latency reduction and energy reduction. And the paper generalizes row clone by also doing not only intra-subarray copy, interbank copy, but also you can do inter-subarray copy when they are in the same bank. One only problem with this is that the inter-subarray copy, when it's the two subarrays are in the same bank, needs to happen through two interbank copies. And that's what makes this operation the slowest one in the generalized row clone. But still, and actually that's what you can see here, that there is not really improvement in terms of latency for the inter-subarray copy, but still there is improvement in terms of energy. But especially good and especially fast and energy efficient is the intra-subarray copy, as you can see in this plot, with more than 11 times latency savings and more than 74 times energy savings. And row clone can also be used for initialization. You just need to reserve some rows for the values that you want to use to initialize, like for example, a row of all zeros. That is a very small loss in terms of capacity, and initialization as well as copy are frequent and some frequently used in some important applications like the ones on the slide, as you can see. And for those applications, we can see quite interesting end-to-end performance improvements and energy reductions. You can check more details in the paper or also in some of Onur's lectures, like for example, this one. So this is a generalized row copy, and remember, what's the biggest issue with it is the inter-subarray copy. The inter-subarray copy is a problem because you need to do the interbank copy twice. So that's why in HPCA 2016, our group proposed a way of copying data from one subarray to another subarray when they are in the same bank. And the key idea was placing isolation transistors that connect bit lines into consecutive subarrays. And by activating these isolation transistors, whenever you want to perform the copy, it's possible to move one entire row from subarray 1 to subarray 2 or vice versa. And this allows fast bulk data copy from subarray to subarray, as well as other interesting applications as well. So that's the LISA paper, as I said, from HPCA 2016. And a few years later, we published this Figaro work that allows us to do something similar, but at a much fine grain granularity, by making use of the global row buffers and by making use of the global bus that connects different subarrays inside the same bank. Later work on these kind of proposals are the in-memory bulk bitwise operations and the ambit work that also Onur introduced in the morning. The key idea in the ambit work is to activate 3 rows at the same time, assuming that we can do that in a real chip. It will be, if it's possible to activate 3 rows at the same time, 3 rows in the same subarray at the same time, this is the same as performing a majority function. And that's what you can see in this slide. We first do this activation, 3 rows at the same time. The 3 of them start sharing their charge with the bit line, producing a perturbation in the bit line. And at some point, when we enable the sense amplifier, the bit line is pulled to the majority of the cells A, B, and C. So if you have, for example, here, 2 of the cells are completely charged and 1 of them is completely discharged, the result will be VDD, will be 1. And that's the basic idea of the ambit work. And by using this basic idea, it's possible to implement bulk bitwise and OR, because and OR are basically the same as a majority operation where one of the inputs is fixed to 0 or to 1, as you can see on the right-hand side of the slide. The ambit paper proposes very minimal modifications to the subarray organization. Basically, the only thing that you need is to have some small row decoder that is able to activate 3 rows at the same time. and because doing that for the entire subarray would be much more costly in terms of area for the row decoder, the proposal is to just enable some of the rows as compute rows. Only some of the rows are connected to this bitwise decoder that has the ability to activate 3 rows at the same time. So basically, and as you see, this can be achieved with very little overhead. So in order to use this ambit substrate, then it's first necessary to copy using row clone data from the other rows that are just storage or data rows, from those rows to D1, D2, D3 that are the designated rows, those that are going to be used for computation, those that are connected to this special row decoder, and then activate the 3 rows at the same time, and finally store the result in the destination row. So that's the basic idea that was first presented in this CAL paper in 2015, but still there was one operation that was missing in order to be functionally complete, because with and or you can do things, but you cannot do everything. And what was missing was not the inverter, right? So the idea later presented in the ambit paper in 2017 was including one row, at least one row of dual contact cells, such that, as you see, this cell has 2 access transistors. One of them, same as any other cell, is connected to the bit line, but the other access transistor that is controlled by this N word line is connected to the other side, to the bit line bar, basically, to the other side of the sense amplifier. So this way, whenever you have some value here in the bit line, it will be inverted by this inverter in the sense amplifier, and the inverted value, the bit line bar value, can be taken when we activate the N word line and be loaded into the capacitor, right? So this is the basic idea in the dual contact cell. Here you can see in a little bit more detail, and also in this figure from the paper, how this in DRAM NOT operation can be implemented. This is one potential way. You may come up with other ways of doing NOT inside the DRAM subarray, but now that we have AND, OR, and NOT, it's possible to implement much more complex operations, arithmetic operations that can be using more, even more workloads. The ambit paper already showed very good throughput for bitwise operations and a lot of energy savings, and also for some real workloads like bitmap indices, bit weaving, etc. They also showed some good end-to-end performance improvement. But yeah, you can check the details in the papers or in some of our other presentations. I wanted to introduce this before we go for lunch, which is the time right now, and I don't want to delay anyone. After lunch, we will continue for a few minutes in order to cover this framework for processing using memory in DRAM that makes use of ambit and makes use of row clone and proposes a way of implementing more complex operations inside DRAM, operations that could be created by a user and later used in any real program. So yeah, thank you so much for your attention. That's all for now. We will continue later.